This is an introduction to significant digits. Although you've probably learned some of these things before, this should largely be review, with maybe a few new items. Here's some review on unit conversion first, though. So question 1, 3 mu m in meters. So that's 3 micrometers. So which of these would be correct? Micro means 10 to the minus 6, so 3 micrometers is 3 times 10 to the minus 6 meters. Number 2, what is 2.5 hours in seconds? Well, to do that conversion, remember that there are 60 seconds in a minute and 60 minutes in an hour. So 2.5 hours times 3,600 seconds per hour, and 2.5 times 3,600, we get 9,000 seconds. What is 65 kilometers per hour in meters per second? Well, 65 kilometers per hour times, well, we want to cancel hours, and so we have 1 hour in 3,600 seconds, and we also have 1,000 meters in 1 kilometer. And so we see here we end up with meters per second, so multiply by 1,000, divide by 3,600, and we get 18 meters per second. There's a shortcut, of course. Looking at that multiplication, we could have just taken 65 kilometers per hour and divided by 3.6. This is a conversion we do a lot, so in the future you'll probably want to remember how to use that shortcut. Significant digits and our pal Gus. Hi, Gus. Whenever we make a measurement in science, we have to be careful to note the precision of the measurement. So the precision of a measurement is shown using the number of measured digits that it contains, and that depends on the tools that we use to make the measurement. Here's an example, 12 centimeters and 12.0 centimeters. 12.0 centimeters is a more precise measurement, so we probably used a different tool to measure 12.0 centimeters than we did to measure 12 centimeters. We may have used a ruler that shows millimeters for the 12.0 centimeters, but maybe to measure 12 centimeters we used a ruler that only shows centimeters. You can't assume that 12 centimeters means 12.0 centimeters exactly. It could have been 11.8 centimeters or 12.1 centimeters, but then it was rounded based on the tool that we use to make that measurement. Any measured digits are called significant digits. And there are a set of rules that we use for significant digits in science. But to summarize the rule, there's kind of an easy memory trick that I use, and that's dot right, not left, where the dot means a decimal place. So dot right means if there's a dot, if there's a decimal place, read the number to the right, and if there is not a decimal place, you read the number to the left. So if the number has a dot, we start at the first non-zero digit on the left and count to the right. So what that means is, if there's a decimal place, read the number to the right and start counting, but never count lead zeros. These are lead zeros if I'm reading the number to the right. I'm reading it this way because there's a dot, there's a decimal place. So how many significant digits rather do we have here? Okay, we're starting here because we don't count the leads, and we're counting this way, and we get 2 significant digits. These don't count. Those are lead zeros if I'm reading the number to the right. I don't count them because they're just placeholders. This brings me to another important point. It's really important that you write down the 0 before the decimal place. If you just write this number as decimal 0051 kilograms, that is not a good idea because decimal places are really small and it's easy for me to miss that. So this really is not a good way to write the number. That's poor form. So do not write it like that. Always include the 0 in front of the decimal place if you're writing a small number. Writing a measurement as 0.0051 kilograms instead of 5.1 grams doesn't make it more precise. You have the same number of significant digits in each case. Let's try this one. Here we've got a number with no decimal place, so here we're using the not left. So we're going to read the number to the left, and we're not going to count the lead zeros, which in this case are on the right-hand side. So how many significant digits do we have here? We start here, that way, counting as we go. So 3 significant digits in this case. To show that a place-holding 0 in such a number was measured, because sometimes we have that case, we underline it. So if we underline the number like this, because we know that it's a significant digit, we know that we did measure that digit, then we put a line underneath the number. So now we have 4 significant digits for that number. Or we could write the number in scientific notation. So 3.080 times 10 to the 5 joules also has 4 significant digits. If we have a decimal in the middle of the number, every digit is significant. So this isn't a new rule, it's the same rule as dot right. It's still dot right again. So we go back to dot right because there is a decimal place right here, and we read the number to the right. So we count 1, 2, 5, and 0, they all count, and we have 4 significant digits in that case. So we don't have any lead zeros in that case. If you measure a 0, you must write it. So your data table shouldn't look like this. Can you see an error in this data table? All of these values we assume are measured with the same device, which means they should all have the same precision, which means they should all have the same number of decimal places. So that one doesn't make any sense. Should look like that. This table makes a lot more sense because now all our values show the same precision. That is, they show the same number of decimal places. Data tables should also not look like this. Same idea, except now one of the values shows a greater precision than the rest. Can you see which one? This one. So that doesn't make sense. So we don't use decimal 5 to mean about half. 0.5 means that the measured value is closer to 0.5 or to decimal 5 than to decimal 4 or decimal 6. Let's try some. How many significant digits are in the following? 25 watts. 2 significant digits. 60 kilometers per hour. 1 significant digit. 305 Kelvin. 3 significant digits. 3.6 kilograms, 2 significant digits, 5.0 millitesla, those are units for magnetic field, 2 significant digits, 0.1 newtons, 1 significant digit, 502,500 calories. Those are some units that we use for energy. We'll talk more about those later. 4 significant digits. .10 amperes, 3 significant digits, 0.017 hours, 2 significant digits, 102.5 megahertz. Those are units for frequency, as in radio signals, for example. 4 significant digits, 2,100 kilojoules, 2 significant digits, 250.0 ohms. Those are units for resistance, electrical resistance. 4 significant digits, 60.80 kilograms. 4 significant digits, 0.0018010 kilometers. 5 significant digits. When we have measurements that are used in calculations, the final answer can't be known, can't be shown rather, to greater precision than the original measurements. And that would be like cheating. In the example that's crossed out here, we see that we have 4 meters divided by 3 seconds, so each of those values has 1 significant digit, and yet we've shown an answer that has 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. So we've gained a lot of precision there, which doesn't make sense. So our answer has to show the same number of significant digits because we've divided those numbers. So we round to 1 meter per second. So for multiplication and division, our final answer, after multiplying or dividing, has to have the same number of significant digits as the least precise measurement. In other words, we check to see which of the initial values has the fewest significant digits, and then we make sure that our answer has that number of significant digits. In this case, we have 1 significant digit for this value, so that's the one that limits our answer. So our answer has to have 1 significant digit, which it does. If we have a constant in an equation, or an exponent, or some numerical factor which never changes, then those don't count towards significant digits. So a half in this formula is not a measurement. Let's try some practice. 7 meters times 7 meters. That's equal to 50 meters squared. Don't tell your math teachers, they won't like that. But we have 1 significant digit in each of these measurements. 1 significant digit, 1 significant digit, so our answer has to have 1 significant digit. So we round it. 7 meters times 7.0 meters. Also 50 meters squared, because we still have a value that has 1 significant digit. In the next one, each of our values has 2 significant digits. So now our result is 49 meters squared. So each of those values has 2 significant digits. Try these. Round each number to the given number of significant digits. 4,080 joules to 1 significant digit. 4,000 joules. 4,080 joules to 2 significant digits. 4,100 joules. 2.715 kilograms to 1 significant digit. 3 kilograms. 2.715 kilograms to 2 significant digits. 2.7 kilograms. 0.987 volts to 1 significant digit. 1 volt. 0.987 volts to 2 significant digits. 0.99 volts. Let's try these ones. 13.5 newtons to 2 significant digits. 14 newtons. 12.5 newtons to 2 significant digits. 12 newtons. Here we're using what we call the rule of 5. If the first digit to be dropped is just a 5 by itself, then we round down if we have an even number before the 5, and we round up if the number before the 5 is odd. .51 newtons to two significant digits would be 13 newtons because 0.51 wasn't by itself. 0.51 is clearly bigger than 0.5, so we round up. 100.5 kilometers to three significant digits. Using the rule of 5, we have to round it down, so it has to be 100, but we know that it has to have three significant digits, so we have to draw the line under the second 0, or we can write it with scientific notation. Speaking of scientific notation, let's try and write these with scientific notation. 20,450 calories, 2.045 times 10 to the 4 calories. Notice that I have to have the same number of significant digits regardless of the notation that I use to write the number. So I have to have 4 significant digits in each case. 1,200 newtons, 1.2 times 10 to the 3 newtons, 0.235 joules, 2.35 times 10 to the minus 1 joules, 0.09030 kilometers, 9.030 times 10 to the minus 2 kilometers, 0.0000007 seconds, 7 times 10 to the minus 7 seconds, 20.5 kilohertz, 2.05 times 10 to the 1 kilohertz. If we're adding or subtracting, then we're not counting the number of digits, but we count their place. In other words, we count the number of decimal places. So we round our answer to the same place as the least precise measurement. So here we can see that this measured value has the fewest decimal places, so that's the least precise of our measurements. So our answer has to have 2 decimal places as well, like so. Let's try some practice. 7 meters plus 7 meters. Well, each of our values has 0 decimal places, so our answer has to have 0 decimal places. 7 meters plus 7.0 meters. This value still has 0 decimal places, so our answer still has to have 0 decimal places. 7.0 meters plus 7.0 meters. Now each of our measured values has 1 decimal place, so our answer has to have 1 decimal place. That's an important and a tricky one. People will often leave the decimal 0 out here, but we can't. We measured those values and we know that we have to have 1 decimal place. So you should be careful with that one. When you're solving multi-step problems, it's important rather not to round too soon, because that could affect your calculations in your subsequent steps. No, really, I'm serious. Don't round too soon. Here's our pal Gus, handsome fellow, and he helps us to solve problems. And Gus helps us to remember that when we solve problems, it's a good idea to write our given values down, write down our unknowns, then we select an equation based on the givens and unknowns that we have, and then we solve using that equation. So here's our procedure. Given values, unknowns, select the equation, and here's the thing. Make sure that you're selecting the equation based only on the givens and the unknowns. That's how he helps us. Then we're going to substitute and solve using that equation. Here's an example. How long does it take an object to travel, traveling at a speed of 3 meters per second, 3.0 meters per second, to travel a distance of 1.5 kilometers? So we'll write down our given values first. We have the speed of the object, 3.0 meters per second, and we have the distance, 1.5 kilometers. Notice that we write down the variables using the symbol for the variable. So I write down v because that's a symbol for speed. We don't write down the word speed. That way it helps us find the equation that we need to use. It's important that we convert all of the values to the standard SI units as well. So instead of kilometers, we're going to convert that to meters. Time is our unknown, so we'll write that down. Now we need to select an equation that has speed, distance, and time in it. And this we've seen before. Speed is equal to distance divided by time, or distance over time. We'll rearrange that. So we want to get delta t by itself. So time is equal to distance divided by speed. So we get time is equal to 1,500 meters divided by 3.0 meters per second, and we get 500 seconds. But we have to express that with the correct number of significant digits. It takes the object 5.0 times 10 to the 2 seconds, or 8.3 minutes, to travel that distance. All right, now you'll have a chance to do some practice on your own.